Hello everyone, this is a two-dimensional ANSYS Fluent combustion on a high-pressure burner. The burner has a premixed flow and two co-flows. Actually, I have already done the simulations and here I am going to show you the conditions and processes that I used. Firstly, into the geometry. I have used a rectangular domain with a chord section indicating the region of the disc that stabilizes the flame. Note that for 2D axis symmetry conditions, the axis of rotation should be pointing on the x-axis direction and the model should be drawn on the positive y-axis. Now let's move on to mesh. For mesh I have used edge sizing and face meshing and provided different number of divisions for each sections. Now you can see the inlets and outlets for my domain. This is the air fuel inlet, this is the air inlet, this is the axis of rotation, this is the word that separates premixed flow with the co-flow, and this is the nitrogen inlet, this is outlet, and this is valve conditions. Actually I have divided the disc part into different sections so that I can provide different temperatures to the different disc parts, and it is quite useful while changing the flame conditions. Now let's move on to the setup. Let's first check the mesh quality, and we can notice orthogonal quality and skewness and aspect ratio which are within the ranges. Now move to models. You can turn on energy. You can use K epsilon standard model. In the species section I have selected partially premixed combustion and I have used C equation as a premixed model. You can also use extended coherent flame model, but I have used C equation because it is the standard one. In the chemistry section I have used 10 bar operating pressure. I have turned on non-adiabatic conditions. The fuel stream reach flame limit is changed to 1. This is the place where I can give the fuel inlets, fuel values, fuel and oxidizer values according to the equivalence ratio. In my case, this is the rich flame with the equivalence ratio 1.2. Then go to table, calculate PDF table. It will take some time. Apply. Okay. File, export, PDF. Okay. Now I have created a new material called steel. This steel is the material given to the discs. In the boundary conditions I have given mass flow rate conditions that I obtained from the experiments. In the species section you can change the mean mixture fraction to 1. For your inlet, mass flow rate and species values to 0. This is axis. I have not used any nitrogen inlets. For outlet, species value of 1 is given to backflow progress variable. And these are the wall conditions given to the discs, and for now I have used 1000 Kelvin. Now moving to solution section. Change everything to second order upwind for better convergence. Under solution controls, inside equations, you can uncheck premixed combustion and PDF. Set the convergence criteria of your choice. Now then initialize. I have used hybrid initialization. Now run calculation. I have used 4000 iterations. Now adapt a region for premixed combustion. This is the area in which the premixed combustion occurs, and usually you select the region near your fuel inlet. You need to mark down it. Then go to solution initialization and patch the area. Then to solution controls, under equations, check premixed combustion and PDF. For better results, I have decreased the convergence criteria and increased the number of iterations, and left it for convergence. After letting it run for 5 hours, I am stopping the simulations. Now moving into the result section, you can observe contours of temperature, pressure and species concentrations. Few I am going to show you here. This is the absolute pressure. You can see 10 bar is evenly distributed. Velocity contour, maximum is at the edge of the disc. Now the mole fraction of weights. Here you can see nice little region in between the premixed flow and the co-flow, indicating the region of stoichiometric. Showing the region of incomplete combustion. Yeah, this was how fast or slow the reaction is. And you can plot the mole fraction distributions of OH. This is at 4 millimeter above the burner surface. This is how the wedge distribution looks like. Okay, this much for today. Thank you very much for watching. I hope it helped someone.